Well, this is a kind of a surprise because I expected AJ to give this talk, and at the very last minute I discovered that it's me, and so we decided to combine material from the work it does in the US with my additional stuff. So and this explains. This explains some contributions there. This story starts in 1976 when the Fred Walsh measured minus 210 dBc, and he didn't realize that this was lower than the thermal floor. And he didn't realize that something could be really wrong under the hood. Then we had around 1980, 1999, we had some experiment where we realized that it is possible to measure the noise below the thermal floor. It's the noise of two Porch components. But at that time, I never thought about measuring an oscillator. Application to oscillators with the cross spectrum came from NIST, mainly Craig. It seems that he's sick at home, and Archita is here. And they did some outstanding work spotting problems in oscillator measurement, real problems, and finding some solutions. And then we had some workshops in the past year, and we hope we can get another workshop on this cross spectrum next year in Besançon. Now let me go on. The problem shows up from this kind of oscillators. This is a remake, a modern version of the very ancient scheme, well, not really ancient, but the first scheme where Ulrich proposed to get the signal out from the current flowing in the quartz instead of regular collector output. And this solves spurious harmonics, harmonic distortion, and so. And this works around the thermal noise because important, the motional resistor is not electrically coupled to the buffer. So, working well with electronics, the noise is mainly limited by the collector resistance plus some contribution from the internal distributed base resistance and so on. This is the Giacoletto-Gummel-Poon model. But this term can be attenuated in some way. So when we have an oscillator like that, the noise can be really, really low, and problems come out. For example, I just download from the net a spectrum like this. This is just a portion of a spectrum. Instrument and oscillator and whatever just don't matter. The point is that this number translated into a temperature, into an equivalent temperature, is of the order of 700 kelvins. And this is probably too low, and this hides mistakes. It hides mistakes, of course. Then the other source of trouble is the dual mixer scheme. This absolutely fantastic scheme coming from NIST. I do not remember exactly where it first appeared in the oscillator version with the two references there. But anyway. Anyway, and there is something given by Archita just afterward on this scheme. But anyway, we have trouble from AM noise because AM noise can be positively or negatively correlated. And if you flip the phase, AM noise keeps its sign, then we have some impedance problems here, and we have the energy of the dartboard. But we go on. These measurements were then were done in Patterson with the 100 megahertz oscillator here, and we observed some weird behavior, but I would just go very short in this. The next one is more interesting. This is just a phasor shifter in the line between oscillator and the input power splitter. And just adjusting the phase, some weird behavior can be observed. Not really understood, but this was measured with a 2.4 megahertz surface wave oscillator. Another strong warning comes from metamaterials. People are excited with metamaterials now because we can implement epsilon, negative mu, or both. But impedance with the metamaterial, impedance is something totally different from we are used to. And this when a metamaterial filter is inserted between the oscillator and the instrument, well, I dare to say everything goes to the hell. We have different filters, and the results are just too different. Now, just to take a quick look to the instrument, what it does. The instrument, to quick review of the mathematics. We have here a common signal from the device under test, and two signals A and B. We write what the cross spectrum does, Fourier transform, 1 over acquisition time, y Fourier transform of that, times x Fourier transform of that complex conjugate. Then expand x and y as real and imaginary part, and then further expand x equal common plus a, y is common plus b, and so and so. Then you have a full page of equations, but just keep colors in mind. Important is yellow because it's the background of the instrument, and blue or cyan, that is the device under test noise. And then the important point is that all the useful signal, which is the device under test noise, goes in the real part. Then the noise of the instrument is equally split between really and imaginary part. So we can even use the difference between really and imaginary as a monitor, as a health monitor. But it's important to observe this point, and the noise of the instrument just goes. Then when we have in mind all this thing, we learn a lesson from Johnson thermometry or from radiometry or so. People measure the equivalent temperature. So we did an experiment, and if you want the details of this, there is a poster tomorrow. The idea is that the power splitter does sum and difference of two signals, and just working on equations, you notice that the expectation of the cross spectrum, the mathematical expectation, is proportional to the temperature difference. The difference between the equivalent temperature at the output of the device under test and the temperature of the dark port. And this is a big trouble. We can correct for the temperature of the dark port, but we need a very accurate model of the power of the loss inside of the power splitter. And anyway, this was published at NBS in 1962. I was 5 years old at that time, and it's a very well-established science. So doing this experiment, instead of having oscillators suppressing the carrier and so on, I just did an audio frequency mock-up showing where troubles are. So this is kind of Johnson thermometry, but I inserted a filter at one input. Here inserted a filter, and this is a true hardware simulation, so a mock-up of what happens when you have an oscillator where the signal comes out from the resonator. So the power splitter is coupled to the two resistors, was coupled to the two resistors at the room temperature. When you observe the resonance frequency there, and the cross spectrum is 0 because everything is at the same temperature. And you see the real part is 0 here. Out of the resonance, the resonator is just open circuit, but the resistor is not coupled to the directional coupler. Only this contributes, and we have a fully negative correlation. Of course, if you monitor the absolute value of the cross spectrum as people do, you observe a dip like this. But this tells only a small part of the story. This is much more scaring because the cross spectrum is negative everywhere, which means an imaginary number of radians per square root of Earth. No, not for me. Not for me. Anyway, go on with this. Another part of experiment is about amplitude noise. This is a true experiment with a 10 gigahertz synthesizer, 2 mixers, and so on, and no device under test, a short cable, and it has no phase noise. 4-inch semi-rigid cable has virtually no phase noise. So the one and only common signal that is fully correlated everywhere is the AM noise of this guy. And this appear to be positively correlated or negatively correlated, depending on, 15 minutes, depending on what you do with these phase shift. Then, I think this is the one, PDF numbered, put numbers even to skip the slides. Weird. Anyway, we are at the very last slide. This is a conclusion. Instead of just repeating a summary of what I said, I just open a different view on the whole thing. Read the BIPM document, the International Vocabulary of Metrology. The Vocabulary of Metrology defines the A-type uncertainty something like noise. You can play with the statistics. You average 1 billion of a spectra. You kill the noise by the square root of 1 billion, and that's it. The B-type uncertainty comes from the system, and it includes all of the weird phenomena I mentioned, plus other weird phenomena I even not suspect that they exist. And this cannot be reduced getting data, more and more and more data. Exactly as when I buy a pound of meat, I cannot improve precision by weighting 1 million of times the same piece of meat. This is a system uncertainty, and then they can be combined. But then, when you forget system uncertainty and you pretend to reduce, and so on, it happens that the quantity, including uncertainty, hits 0. But the phase noise spectrum is inherently a positive quantity, and again from the vocabulary of metrology, you read that when the uncertainty interval of a quantity that has to be positive is 0, you change term, and the term 0 uncertainty applies. You have to say, I measure nothing with 0 uncertainty, and this is uncertainty assessment. And that's, I finished 18 minutes.
Very time.
Thanks for being here.